semester. And today, I mean, Sumyan, he sent a very kind email with expectations, and I'm kind of, I don't know where to hide. But anyway, let's try to do it. So I will try to do very basic things, but I hope that we will arrive to possibly new concepts. I'm not aware of what you know. So usually magnetism is kind of advanced topic in the curriculum. And have you had magnetism courses? Yes, okay. Do you know what magnetoelectric coupling is? Who knows what magnetoelectric coupling is? One. Okay.
Maybe not me.
Two.
Yeah.
One, two,
Yeah.
1.5. Okay, so some people know, but I hope at the end of this lecture, when you leave this room, more than 50% will know it. I hope. This is my goal. Okay, right. So what I would like, and I will talk about the Mott insulator, so non-conducting metal. I mean, this is not a metal, this is usually transition metal oxide, which where the electrons localize, and there will be some degrees of freedom, electrons, with spin, and then these spins will interact. I will talk about the spin orbit coupling, which will induce anisotropies in the exchange. And I hope to be able to tell you that this spin orbit coupling will also induce coupling between the spin degrees of freedom and the electric polarization. And maybe, possibly I will take a break and then we can, I mean, I would like also to show you some slides with experiments. And for that, I will need this thing here, the screen. But yeah, so this is kind of either screen or black hole, so maybe we will set it up during the break or we'll see.
Yeah.
Okay, so let's start. And some colorful stuff here, very good, excellent. But okay, so first, where does the magnetism come from? I mean, usually we have learned in the electrostatics that if we have two magnetic moments, like this and that, then there will be a dipole-dipole interaction, classical electrodynamics or electrostatics. Between these magnetic moments, it will be, so it's good, this is being recorded.
Don't worry about the recording.
Right, so you will have something like mu1 dot, these are the magnetic moments, something like this, minus mu r1 to mu1. I think this is it. So this is the distance between the two things. This is r1, 2, and this is divided by, this is my, yeah, okay. Maybe something like that. Please correct me if this is wrong. So this would be an interaction which is not isotropic because we have this position of the spins in the real space. And you may wonder whether this is enough to order the spins in some material. Now, if you check with the numbers, it turns out that this strength is very, very tiny. It's less than a Kelvin. I mean, this goes quadratically with the length of the spin. So we have some large spin magnets like F electron systems. They have like 7 halves, 9 halves, whatever. They have huge spins. And there are some materials like the spin ice. In spin ice, that is I don't think that, maybe some of you heard about spin ice. So essentially, those are F electron spins sitting on tetrahedra. In that case, this becomes kind of important. And for this large 7 half or whatever, 9 half spins, the strength of this is a few millikelvin. So this is like few Kelvin for like F electron systems. F electrons like I would say 7 half or 9 half. I forgot the precise value. So these are huge spins and few millikelvin. If you scale this back down, I mean this is experimental, kind of experimental measurement. And if you scale down to spin 1/2, means that 7 to the square is 49. You need to divide this by 50. You get that it is really tiny. And usually what we observe in the materials is that the ordering temperature is a few hundred or maybe few thousand kelvins, depending on what material you look at. So clearly, this is not the origin of the interaction in the Mott insulator. I'm telling Mott insulator. What is the Mott insulator? So suppose you have a transition metal oxide, for example, like lanthanum copper oxide, and materials conductivity. So these are the coppers here. There are also some oxygens here, but let's go for the minimal model you can think of. So there are some orbitals, like p orbitals of the copper, sorry, d orbitals of the copper, like this. And there are some electrons that are distributed on these orbitals, and then we would like to write down the Hamiltonian, what they do. So certainly they can hop from one side to the other side. So that would be the minus d sum of a theta here. This is the side I, j, side I, j, plus we add the Hermitian conjugate part, Cj, Ci. All the spins here hop with a, during the hopping there is nothing happens to the spin. It just hops keeping its direction. There will be cases when this is not so. We will talk about that. So this describes a time-binding model. The electrons can delocalize, they are happy to move and visit their neighbors and so on. However, there is another term, the Coulomb repulsion, because if there are two electrons sitting on the same side, so like this is a d orbital, and then we have one, and the neighbors comes and visits you, then maybe it depends on the details. Maybe there's attraction, maybe there's a repulsion, and for the electrons, they have charges. They are repelling each other because they have the same charge. So there is a plus u times n I squared, or maybe n I up, n I down. So in case that there are two electrons, then there will be a large repulsion between them. Now, what it will cause? It will cause that we would like to have a system where typically we have like, if it is less than half filled, if the number of electrons is less than the number of sides, then the electrons will hop around, but it will be rarely happening that two electrons hop on the same side. If the number of electrons is the same as the number of sides, in that case, every side is occupied by a single electron, and it can't really move. It can move to the neighbor, but then it will cost a large energy U. It needs to invest energy. But then this is a highly excited state, and you would like to fill as soon as possible this, so it will hop back. So somehow one electron cannot really propagate and go to the center. So these are the Mott insulators. What I'm telling you is a very simplified, naive, and so on, but probably sufficient for the reason for today. Okay, now suppose that we have this model, and let's look at two sides. And maybe this is also fine. So we start from this here. Then this guy can visit the neighbor, and when it visits the neighbor, this here. If you have any question, please feel free to interrupt me at any time. So there are no stupid questions. Yes, please.
So you are mostly considering one-dimensional.
It seems like a draw. It seems like a draw. Yeah. But 1D is special. So what I try to draw here, there are some special features of 1D that are not present in 2D or 3D. And 1D is a particular corner of physics. And then it can be also realized that there are experiments like you put one electron, and then they charge and spin will, they'll collide. The charge will be here, and the spin will propagate in different directions. And so there are many interesting physics going on about the system. But I'm not talking about that. So this is the initial state. Then suppose that we have that this guy visits the neighbor. Then it will become an excited state with energy U. This is the hopping amplitude T. And they have a choice. I mean, either the same guy, so this was the upspin up here, it can go back. So we have a arrow like that. Or what can happen is that the other spin decides to go back to that side. And then what will happen is that we will have this situation here. So essentially, we are a ritual process. We swap the two spins. So up, down becomes down, up. The energy of this guy is U. And using the second order perturbation theory, we learn that during this process, essentially, we gain T squared over U energy. Now, when do we gain this energy? So, we needed these two guys to be on the same side. If, in case we have two spins that are pointing in the same direction, those two guys, they cannot hop onto the, I mean, this guy cannot visit him because there is a Fermi exclusion principle. Pauli. Yeah, these are fermions and there's a Pauli exclusion principle, so it is not possible to visit it. So, if the electrons are in a triplet state, it is not possible to gain this energy. They will gain this energy only if they are in a single state. So, if we have a singlet on two sides, we gain this energy. If they are in a triplet, they will not gain it. Okay, so let's try to write this using kind of a projector.
You can find one singlet.
Yes. Right. So, these are spin one half objects. So, to describe the spin one half object, we use the spin raising, lowering, and those operators. So we have the Fx, Sy, and Z, and they satisfy the usual algebra. And Fx, Sy commutator is I and Z. Again, I'm not sure plus or minus, but if you are consistent, then this Sy, Sz is, you see, it must be I times. You do the cyclic rotations, and then you get the rest, and then you don't make a mistake, and then you will be consistent with yourself, at least. Right. You have this commutation, but then it is. So this would, I mean, like, if we have a wave function, and we would like to know in what direction the electron spin is pointing to, then we just take the wave function and we take the sandwich with any of those operators. Spin is, you can watch YouTube videos about the spin. It's some inherent property of the electrons. It comes out from the, I don't know. I don't know what is electron spin. Let's make it short. Right, but it is there. It is present. And if you look at the Dirac equation, the solution of the Dirac equation gives you the spin one half of the electron. The spin one half is maybe depending how far we go, maybe I will tell you a little bit more about the properties of spin one half electron. But nevertheless, it tells us roughly that the spin is possessing in some diversity. Sorry, it has some angular momentum. It is conserved quantity. And whenever you have a charge and you have an angular momentum, you can think that if you have a rotating charge, it will have a magnetic moment. So there is a magnetic moment associated with the spin that is roughly proportional to G factors. I think there is some maybe Bohr magneton, and here is the spin value. So the electric moment of the spin is proportional to the electron spin operator or expectation value as you wish. There is this G factor here, which would be 1 for usual orbital moments, angular momentum, but in case of the spin, it will take G electron equals 2, and this is related to the fact that these are relativistic objects, and this comes out from the Dirac equation, and I think there are some corrections with this too, and then particle physics or field theory, they calculated these two, I don't know. There is some number here, and the calculation and the experiment matched very nicely. So this was one of the success stories of physics. The quantum dynamics that they predicted what is this number here. Anyway, so electron has this G equal to 2. Magnetic moment is proportional to spin. And then we would like to work with this guy. So we introduce S plus, that is maybe this S minus, maybe this operator. These are kind of raising and lower operators. And whenever we have the spin 1/2, it will have like 2 components. It will have the up spin, which is the Z equals plus 1/2 component. That will be the down spin. That will be Z equals minus 1/2 component. Then if we apply S plus and S minus, what they will do that the S plus will just raise the spin that is pointing down to up, and the S minus will just lower the up pointing spin down, and then the NZ operator acting on up will give you 1/2 times up, this is diagonal, and the NZ on the down pointing spin will be minus 1/2 down. Okay, so we have this relation. If we have 2 spin 1/2, then we can use the usual rules how to add momenta. So we have a 1/2 electron, and we have another 1/2 electron. Then you learn in quantum mechanics that additional 2 1/2 will result in a spin 0 object and a spin 1 object. So this is the addition of the angular momentum. Right. So let's try to figure out what is this 0 thing here. So we have, the total spin would be S1 plus S2. This is for the first electron, this is for the second electron, and we have beta here. This, the sum, it will, let's call this, let's just call it S without the something here, S alpha. The sum,
You mean S alpha beta? Okay.
So the sum will also satisfy this commutation relation. So we can also introduce S plus and S minus, that is equal to S1 plus S2 plus S1 minus S2 minus for the total spin. S plus, when acting on downspin, it raises the spin. If the total spin is equal to 0, there is nothing to raise. So we need the wave function of this guy here is something where if I act with the S plus with this thing, or if I act with the S minus with this thing, it will give me 0. It can't do anything. Right. So it means that we need a wave function where S1 plus S2 plus acting on something that we have and we need to figure out what is this thing here. So we can have like up plus, with some coefficient here, and up down, another coefficient plus down up, down, this here, and it is 0. So we need to figure out what is this wave function that if we put these things together gives us 0. Okay.
What's the population of the up down and the down?
Yes, that will be, we need to arrive to that. Yes, that's right. Okay, so from this equation, what we learn is that we can't have in the wave function this part. This must be 0. Okay, so I delete that part.
You mean up will be 0 from this one?
No.
Because s plus acts.
I mean, if we have a some pair factor here, some condition, if we add with the plus, it will annihilate this, and we have no information about this condition.
Oh, right, that's what I meant.
Okay, so what we get, I mean, if we apply alpha, it will.
Oh, I see. I got what.
Make this up, and we don't want it, so this needs to be 0. This condition.
Right.
So I remove this.
Very good.
Then, if we add with the minus, then it will remove this guy here.
Right.
And then what remains is this up down plus and something times down up. Okay, so maybe we need the next thing, the sz1 plus s2z acting on this wave function to give us again 0. It needs to give 0 because it is the exact eigenstate of the spin. It can only have 0 value. So if I apply the sz, this is sz to this wave function, what we will end up with that the up down needs to be cancelled by the down up, and this is precisely what you mentioned. This is this entangled state of two spins that will be a singlet state. This is very important.
So minus or minus up to a phase will also work?
Up to a phase, yeah. We can have an overall phase.
Not overall phase. Relative phase also
relative
shouldn't work or
doesn't
doesn't work.
It doesn't work. It needs to be,
exactly.
It needs exactly. Yes, please.
So this you have derived is essential from speed algebra.
That's correct.
And that's true always. I think whenever there are speed,
yeah.
I'm going to add that.
Okay.
I'm saying that when you draw this to speed, you have written down an Hamiltonian for that.
No, I haven't yet. Did I?
So I thought that you did Ci sigma, delta Ci, Cj sigma plus the Hubbard.
Oh, that will come. Okay, so at this moment yet, we haven't done anything about the Hamiltonian.
And then you bring these arrows up there and say that there is an energy gain of minus 12.
It will come. This is the next step. So I try to introduce you the singlet thing, and then later the triplets, and we will see that if the two electrons are in a singlet state, they gain energy, and if they are in a triplet state, they will not. So we need the effective Hamiltonian is essentially a projector that will separate the energy of the triplet and the singlet. Right. But yeah, right, okay. Good. So this is a singlet thing. Then similarly, we can find out what is a triplet. And what is a triplet is that the triplet is s equal 1, s plus 1, 0, minus 1. So what we can do, maybe I can delete this part here. And to construct the triplet wave functions, we can, first let us try to find out the sz equal. So this is total spin, this is sz component. So if we apply the s plus to this guy, it will increase the sz, but we don't have where to increase, so this needs to be 0. It means that the one state, if you play the game that we were playing here, it will turn out that this will be just the up. Because this is the state when we apply the additional, the string racing operators will give us it. Once we have this is usually called the highest wave state. We can act with the spin lowering operator to obtain the other spin components. For example, if I apply s minus this one, it will be up, down, plus, down, up. I'm neglecting the normalization factors and so on, they're always there. And this will be the 1, 0 as the different 0 state. So this is almost the same as this guy, except that it is with a plus sign. It is also entangled state. So this is not entangled, this is entangled state, but entanglement maybe has nothing to do with the SU2 representations or more complicated. And then if we apply once more the S minus to 1, 0, then it will lower this up spin here, it will lower the other spin, and we end up with the down down. Okay, so these are the different spins. Now, we need to distinguish the spin triplets and the spin singlets. How to do that? We need some operator that will have different eigenvalue for the triplets and the singlets, and we can use that operator to write that we will gain energy if we, supposing that we are in a single state. Okay, so let's try to do that. If we take the square of a spin operator, that will, the S dot S or S alpha will in fact commute with any of the S alpha. S beta. And this is the sum over alpha, so this is the square of the spin. S is square plus S square plus S square. It will commute with any of the spin elements. Good. So this is called the
Casimir?
Casimir.
Yeah.
This is the quadratic Casimir operator. So the Casimir operator can be used to distinguish the irreducible representation of some algebra. So maybe you have SUN, then there will be more Casimir operators, blah blah. So Casimir operator, very useful thing. The Casimir operator, so the S square, when acting on some string S representation, it will give us S times S plus 1 representation. This is what you learn in the quantum mechanics school, or just accept it. So the S square, if I'm acting to any of those states, any of the triplet states, it will be diagonal, it will give the same eigenvalue, and it will be this value. Here you can calculate it. Okay. Now this S square, in the case of two spins, we have the S1 plus S2, that's why you calculate it. S1 plus S2 alpha times S1 alpha plus S2 alpha. This is the square of the total spin, and it will be equal to S1 alpha plus S2 alpha plus, they commute among each other, 2 times S1 alpha, S2 alpha. Good. This here is again a Casimir operator. It's a number. This is also a number here because it's just the length of the second spin. And this describes the kind of the fact that we have two spins. So the total spin, the Casimir operator, is proportional to a number plus this S dot S. So if we write, so this S dot S is something that takes different value for a string, for a triplet and for a singlet. And that we can use conveniently to distinguish between a triplet and a singlet. Okay? So, this is like some constant plus 2 times S1 plus S2. And this is what we are after. Okay, right? This describes the change interaction between, kind of interaction between the two spins. Not yet there. So we have this thing here. If we use the S plus S minus operators, then what we learn that this S1, S2 can be written as S1Z, S2Z plus 1 half S1 plus S2 minus plus S1 plus S1 minus S2 plus. Here, if we apply this operator to the triplet, say up, this is the simplest one. We can't do anything with this terms. We only have 1/4 times up. Okay. If we apply, and we can apply it also to the up down plus down up or any component of this spin triplet, it will always give us 1/4. Now we can also apply it to the singlet state. Dot S2 up down minus down up. This will give us, from this term, we will get minus 1/4. And from this s plus s minus, what it will do, it will raise this guy, but this is just negative sign of the other term. And so we will get another minus 1/2, the same wave function. So it is minus 3/4 times up, down, minus down, up. Okay. So for triplet, we get 1/4. For singlet, we get minus 3/4. So we want something that will gain energy if this is in a singlet and get nothing if it is in a triplet. So let's just subtract 1/4 here. Minus 1/4 plus this will give us, okay, so this is not right because you are taking me. Are you taking notes?
Some people are.
Some people are taking notes. Okay, okay, okay. Right, so what I mean is that S1 plus times S2, this is this operator here, minus 1/4 will, if I add onto the spin triplet, it will give us 0. If we add this onto a singlet, it will give us a singlet with coefficient 1. So this is a projector onto the singlet pair. So once the electrons are in a singlet pair, we gain energy. So what we will write, that this effective Hamiltonian is nothing else but the effective Hamiltonian is, this is from the second order perturbation theory. Again, there might be some force there, or 2 or 4 or whatever, I forgot. Okay, let's put 4 maybe. Sorry, I don't know. Yeah, right? Then what is important that we will gain energy in case if we are in a single state, so we can just write S1 dot S2 minus 1/4. And this is the effective exchange, effective energy gain coming from the second order process of hopping of electrons, and the fact that this is of this form is relies on the Fermi Pauli exclusion principle that these are electrons. And if we calculate how large this number is, so this U is it can be electron volts, and the hopping, depending on material, can be a few hundred milli-electron volts, whatever. So this number can end up anywhere between, say, 10 Kelvin to, I don't know, almost maybe 3,000 Kelvin. And in the Cook range, there is 3,000 Kelvin. So it gives a much, much larger strength than the dipole-dipole interaction. So this is the origin of the exchange. It is isotropic in spin space because of its nature, and this will usually govern the properties of the Mott insulators.
It's okay. It's okay. We have one more session on Friday, so it's fine.
Right, good. Okay, so this is the basic model of magnetism view. So it originates from the quantum mechanics. So if people ask you, okay, so why is quantum mechanics good? It is good because this will give us magnets, and the magnets, they are in a car, there are like hundreds of sensors built on magnets. So we cannot imagine our life without magnets. Okay, good. So, but I would like to, okay, so this is the basic theory, but then when you do measurements and so on, you find out that the life is not so simple. There will be always some anisotropies. Anisotropies in the sense that maybe this is not S dot S, but maybe some Sx will be stronger than S dot Z, or maybe some other things will happen. And this is the next thing I would like to talk about. So, and it goes back to Dzyaloshinskii and Moriya. And what happened is that there was a material, iron oxide, and again, I forgot the precise name of that material. It's not a magnetite, it's something else, maybe hematite or something similar. it has a lower symmetry than cubic. So this is ion alpha ion 2O3. The crystal structure, it is kind of a, you take a cube and then you pull it apart on the one direction. It's kind of stretched cube, right? And what they observe is that, antiferromagnets, usually this is a very strong antiferromagnetic interaction. If we have two sublattice, then we have some kind of ordering of spins that is, they want to give zero magnetization. That's why they are antiferromagnets. Ferromagnets give a finite big one. Nevertheless, what they observed is there was always some tiny ferromagnetic moment. And it was a puzzle. Why is it there? You have a huge antiferromagnet and then like small moment pointing in certain direction.
So this is an insulator.
And this is a
Mott insulator.
Yeah, it's a Mott insulator. Right. So what Dzyaloshinskii then did was to try to figure out what are the allocations in the Hamiltonian based on symmetry principles. And that's what we will try to do now. We will examine what happens if we have a single bond with the, say, copper here, or UH ion, and then we have extra oxygen that is sitting not in the middle of the bond, but slightly off. Okay, so it is shifted in this direction. It will lower the symmetry of this bond. So whenever we have a Hamiltonian, it shall respect the symmetries of the system. Then we have so we will try to figure out what are the possible. So we have a spin 1 here, we have a spin 2 there, and we can apply certain symmetries. For example, this guy can be, it has a C2 rotation like this. It has also a plane, mirror plane that is in the sigma, let's call it sigma H, inside the blackboard. The blackboard is like a mirror plane, and also we have another mirror plane here. And that builds up a point group, maybe D2 or whatever. It's a group with 4 components.
So this mirror plane is because we have a full three-dimensional crystal. That's why it's important.
Yes, that's right. Exactly. So we need to figure out how do the physical quantities transform under, say, C2 rotation to full rotation or this mirror plane. It's not too difficult. So suppose we have a.
So a nice question,
Yes.
Karlo. So how do we think about the quantization axis of the spins right now?
We will have no quantization axis.
Right now,
we will only have Sx, Sy, Sz. So we will have the spin operators. So, right. So this is x, this is say y,
okay,
and then there will be z-axis,
and we stick to that.
and we work on the operator level.
Okay.
What you are asking is more difficult question, and I don't think that I will have time to talk about that. Right. So
no, but this answers my question.
Okay, simple thing. Okay, so let's try to figure it. So if we have some vector pointing in some direction, what does C2 do? The C2, so we have C2, and we have some vector that is pointing in the x, y, z direction, and we are rotating around the x. If we rotate the vector around x, it will be, it will come here, and if we have a z pointing inwards, it will be pointing outward. So the x, y, z will become x minus y minus z. Do you agree with this?
Yeah.
Anybody saying it's wrong? I will make a mistake in the next one. Right, okay, so we have a C2. These are the x, y, z components, and I will put here x tilde, y tilde, z tilde. This will come here in a minute. So this will become x minus y minus z. Then we have the sigma h. Can you help me? What will sigma h do?
Z2 minus z?
Yes. it will not, it will do nothing to the x and y component, but it will change the z. So what was out, I mean, in front of the blackboard, it will become behind the blackboard.
This is the famous puzzle, right? Like when you look yourself in the mirror, why your left and right get exchanged or something like that.
Okay, I know, don't comment on that.
Oh yeah.
Yeah, right.
Yeah.
Yeah, right.
Yeah.
Right. Yeah.
Yeah.
Right. You talk to Simon about it. Okay, good. Then we have what else remains is the sigma. There is also a sigma like that. Let's call it sigma y z because it is determined by it is in the z and the y axis in this plane. And can you help me what to write there? Sigma xy. Maybe instead of sigma h, I will use sigma xy. And this is c2y. Okay.
Sigma y z you mean or y x y? Oh, sigma h. Got it.
No, you're right. This is y z and this is xy.
Right.
Yeah, good. So what will happen to the sigma x, y, z? Please help me. Not you. Hmm? Minus x. Yes. Minus x, y, z. Good. So we have this transformation. Next.
But if you set the rotation is around y-axis, then will the minus, then will y change to minus?
Thank you. Right. Okay. So we have got this thing here, and you may check that whether they make a group. So, for example, if we apply this and this consecutively, we will get the result. Thank you.
Yeah, no.
After you correct it, it will.
No, the confusion is because in this you write C2y like this, but in that reference frame that is x.
Oh,
So you want to interchange x and y in the reference frame.
Yeah.
So
Okay.
we just interchange.
Yeah, sorry.
No, you can just change x and y in the reference frame. Please check
What do I do?
the reference frame.
Yes.
Just change x and y. Yeah.
That is all?
That now it's all.
Thank you. Okay, very good. Everything okay?
Yeah, now everything is nicer. Yeah.
I'm sorry. Right. Okay, but next. Here, this is a spin. The spin is, so this is what we call a polar vector. These are the usual coordinates. These are polar vectors. Right. A spin is something that is rotating. It's it's not a polar vector, it's an axial vector. An axial vector will have different properties under this symmetry operation. So let's try to figure out first the C2. So I have something that is doing this, and if this is the axis of the C2, I am going to do this. It means that, okay, nothing happened. It's the same as the polar vector. So if we have a C2 rotation, then the polar vector will transform precisely the same way as the axial vector. Okay?
Can you repeat this, please?
Right. So I would like to know if we have an angular momentum. Pointing angular momentum is something that you can describe with
pointing. Okay.
something that is rotating. I have no better
And
way to do it. And then we are doing the seat. I mean, I'm keeping this. This is like, you have the
right.
the rule.
Right.
Left hand rule, right? It's rotating, and this is my axis. This is the y-axis here.
Right.
I'm the y-axis, and I'm rotating on myself.
Right.
By C2, then it will precisely behave. Okay, so this is a polar vector.
Right.
This is the axial vector. They are behaving the same way. Okay. So this is right. Here we have a reflection. Now reflection. So suppose that the blackboard is the reflection plane. So if I try to do this, I need the opposite, the mirror
puzzle. Yeah.
right? So we use the mirror puzzle, and this is what happens. It is rotating in the other direction, so it means that you got it. Right. So what we need to do in this case is that it will just be opposite of the of the polar vector. It will be minus x tilde minus y tilde z tilde, and it will be x tilde minus y tilde minus z tilde. Right. If you were to write as O3, I mean, these are O3, these are members of the O3 group, O3 rotation. O3 rotation includes mirrors and regular rotations. Because O3, the matrices that determinant is equal to plus minus 1. In the case of the regular rotations, the determinant of a 3x3 matrix that describes this thing here, I mean, we can write it, it's just like minus 1, 1, minus 1. This will be equal to plus 1. So this is a member of SO, this is an SO3 matrix. But if we have the mirrors, the determinant will be minus 1. So if we write this, then I should have written. Here I should have written minus 1, 1, minus 1. This is the 3x3 matrix of this transformation here. And here, matrix is like 1, 1, minus 1. The determinant is minus 1. So whenever, and this is the O3, I mean, this is something which is
Determinant minus 1. Yeah.
not the SO3 part, but the
Improper rotation.
Improper rotation. Yes, right. So it has a determinant minus 1, and if it is minus 1, then essentially you need to multiply the polar vector with the determinant minus 1 to get the epsilon bar. Okay, very good. So we learned how they transform. Okay, so let's try to write.
Karlo, one thing. So of course you did an intuitive derivation.
Yes.
But suppose one wants to convert it into an algebraic derivation where it doesn't have to involve intuition. How would you set it up? Okay. Yeah. I guess this basic transformations you have to just set it up like this. You cannot. There's no more further. Yeah. Okay. Okay. Then these are the, I guess, the group generators, and then the rest can be built up. Okay. Okay. Fine.
If you wish, you can look
This
in
is just given.
I mean, that is huge international tables,
Right.
with different space groups, and you can figure out.
Right.
I mean, these matrices are listed. But
So these are the axiomatic rules that we have to start with somehow.
okay. Yes. You are using very strong words.
Yes. I mean, yeah.
Yes.
So suppose I didn't want to think and do this exercise. This is where I have to think. After that, more or less, you don't have to think.
Yeah. Right. Okay. So we need to have an expression that is invariant under those things. So this is how spins transform. So let's try to do let's try to find out what expressions we can write, what is allowed in a Hamiltonian that is invariant under this rotation. Okay, so we have a Hamiltonian that is equal to some S alpha, S beta, and here I write J alpha beta. Alpha beta, the X, Y, Z. Okay. If I write, okay, so there is one more symmetry, that is the time reversal symmetry. Our Hamiltonian, if we are not in magnetic field, or again, in that case, H must be time reversal invariant if we don't break from outside the time reversal symmetry. Spin is something that is rotating in time. If I reverse the time, it will go back. So time reversal will change the sign of the S. And if we have a single S, that is not, I mean, we always need to have even number of S operators in a Hamiltonian if we don't break time reversal invariant. Okay, now, so this is the first, I mean, so here we have the diagonal time, this is the S of S, but let's see what else we have. Okay, so there are many elements, and do it. We can have Sx, 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 Sy, Sx. I haven't really prepared to do it quickly. You know, S, S, Sy. This is 1 and 2, 1 and 2, 1 and 2, Sy1, XYZ, X, so Y, and Z, and I'm in trouble because I ran out. I didn't think my black was actually not very nice, but maybe I stop here for a moment and then maybe we will continue. So first, okay, so we have the sigma yz that is also changing 1 to 2 and 2 to 1. So let's forget it for the moment and let's look only at those guys that are not changing the position of the strings. Okay, so one is the plane, sigma h, and if we apply, okay, let's start with C2. C2 is also a change. Okay, so we have sigma h. Which one is this? This one?
Yeah.
This one goes to 1, 2 goes to 2. Okay? So we try to look at this one. So what it does is that it will change it is not changing the z component, but it is changing the x and y component.
So
Yes.
where is the origin in this discussion?
I did it here.
Maybe there. Okay, fine.
But it, yeah. They all have, they have all respective origins and.
Right, sigma h is not important, but for C2 and not even C2. Okay, I see. Yeah, it's not important. You're right. Okay.
Yes, right.
Yeah.
Okay.
Fine.
Good. So what happens is that here, z is not changing sign, x and y are changing sign. Z is not changing sign, x and y are changing sign. So this Sx, Sz will become minus S1x, S2, S2z. So this guy is not allowed in Hamiltonian. You can't have it. Okay? Oh, good. So maybe we will have something at the end. So this is okay. This is okay. This is not okay. This is okay. This is okay. We can't have this. And then what remains is S1z. X, it is not allowed, and S1z, S2z is allowed. Okay, very good. So we have 1, 2, 3, 4, 5 left.
Under sigma h. Yeah. Under sigma xy.
Under sigma xy. Yes.
This is all left.
So this was sigma xy.
Right.
Next, we need to look at the next one. Which shall be the next one? Really, let's look at the C2. The C2 will exchange the two sides, and so the C2 exchanges the two sides, so it will be S2, S1, X, X, and exchange to minus X. So this is also okay. Right? Good. Okay. So we can have this, no problem. And Sx, S2, Y. What it does, it will move this to S1, Y, S2, X, and there is a minus sign here.
Right.
Okay, change to this here. S1, Y, S2, X will become S2, X minus S1, Y. Is that what is
That's fine.
like this? Essentially, this is the same thing. Okay? Then this is allowed. Then we have that's it. We are done. So we may have this axis like this, and okay, so the Hamiltonian, the terms that we can have in Hamiltonians are S1 x S2 x with some coefficient JSX plus J x J y y x1 y x2 y plus J z z S1 z S2 z plus J x y S1 x S2 y minus S1 y S2 x. Okay. Okay. This is what is allowed. And this antisymmetric part is called a Dzyaloshinskii-Moriya term. I need to see how you write it because in different languages it is written differently. And I think even in the English it is. Okay, so this is why. Moriya is simple. Okay, right. So there is a Moriya interaction which is back here. And usually we call this a dz. So what I presented you here, that was the derivation of Dzyaloshinskii in maybe 58 or 56 or whatever. And later, 58, then later, a few years later, Moriya derived it from a microscopic model. He looked at the spin orbit coupled Hamiltonian, where he had a different crystal levels, different orbital moments, and it was rather lengthy calculation that I will not present you here. I will just present you something much simpler. And he derived also this term, and this term was proportional in first order in spin orbit coupling, and in next order, anisotropies like this, because I mean this will contain the S of S, but there will be also other terms, so-called, I mean these are these metaphors, they arise in second order spin orbit coupling. So usually this is the leading one, and if this is missing, the others become important. For example, in Kitaev model, the Kitaev model, everybody talks about Kitaev model. So that, I mean, in the Kitaev model, what we have, they are like, I will try to show you, it's a honeycomb lattice of atoms that are sitting in centers of octahedron. So I'm trying to show you an octahedron. Am I okay? Right, I'm doing that. I'm doing that. This is for the whiteboard. Whiteboard. This is the octahedron, right? Here we have iridium, and then the next one is like this. Okay, this is the next one, and then you will have the another one below, and then they make the honeycomb lattice. Now, if you look at the symmetries between these two guys, what you see is that there is an inversion center here. Once you have an inversion center, what it does, in inversion center, we haven't talked about inversion center. Inversion center will, okay, so suppose we have an inversion here. What it will do, it will give a minus sign to all the polar vectors, but it will not change the axial vectors. So axial vectors are invariant under inversion, and because of that, there is no Dzyaloshinskii-Moriya interaction. If the bond has an inversion symmetry. So in this precise material, Dzyaloshinskii-Moriya interaction is absent, and because it is absent, then the other guys that are higher order in spin-orbit coupling, they have a chance to show themselves. And then the question of details is that how large they are compared to the
So if I spin off the coupling between this JXY is determined by the relativistic effect,
yes.
or
Yes.
can I get it just because of wave function overlaps? Because the symmetry is reduced by moving this.
Here, you have no idea that,
So,
I mean,
orbital
this is an
overlap?
information that is independent from what I was telling you now. For this now, what we made is that we corrected the spin space. I mean, the spin one half lives in its own system. I mean, coordinate system. It needs to know, when we write this transformation, it needs to be connected to our three-dimensional system where the atoms are. And that's where the relativistic spin-orbit coupling comes into play. I'm not sure if I'm answering your question.
I was just wondering, crystal field, like,
Yes,
yeah,
that's very important.
but that would have a different scale than, so
Yeah.
the number JXY will not have relativistic effects in that case, it will just be but you are saying
this may have. This is crystal field. Okay, I don't know how this number is, but crystal field is definitely important because crystal field is splitting crystal field is giving anisotropic orbitals. This is the crystal field will tell you, will give information to the orbital moment of the orbitals, what is the structure. And once you have once this information of the structure is transmitted via the crystal field to the orbital moments of the electrons, then the LS coupling can select and transfer that anisotropic information to the spin degrees of freedom.
So in this derivation, I guess the lack of inversion center would be apparent if we had the full three-dimensional crystal. Because this is inversion symmetric, right?
This is not.
Why?
Inversion symmetry.
Uh-huh.
Sorry. Inversion symmetry would move this guy here.
Oh, right. Yes.
Okay, very good.
Just out of curiosity, first paper of Dzyaloshinskii,
Yes.
where he discussed about this, was it like based on hematite?
Yes. Yes, he tried to understand why is there a finite magnetic moment in hematite. Very good. So why is there a magnetic moment finite in hematite? So we have a Hamiltonian that is like S of X, and we have this pen in addition. So let's see what will this result?
So we didn't check for the other these things. Presumably this is invariant under that. So we checked for sigma xy and
Yes, we checked because there's a third. I mean, we checked for two of them.
Right.
Suppose that we okay. So if you want to check, this is an error correction. You need to do all.
Right.
And if it is consistent, then you're fine.
Right.
But in principle, and I was counting on you that you will spot my mistakes because these are the generators of the group. This will follow from the two others. So if they are invariant, these two, then it's also fine. But you should check it because you may always make a mistake.
Right.
If it is inconsistent, then you know that you need to check again.
And this is also invariant under time reversal.
This is also invariant under time reversal because we have even number of operators.
So so the Hamiltonian has to be invariant.
Hamiltonian has to be invariant.
So the hematite magnetism with some broken symmetry or how should I think of it if it is time?
We talk about it.
Okay.
Let's do it now.
Please.
Yeah, right.
So just to say, Karlo, that we can go till 12:05, 12:10 whenever. Today,
I think probably we will go. You want a small break? When do you want a small break?
We can take it whenever you suggest, but I'm saying that we can continue this next turn. So there's no hurry or anything. Right. Don't worry about covering vertex models and all that. Yeah.
Okay. So
we cover as much
as with the speed. Okay, good. They seem to be happy.
Okay. So we'll go till when the audience doesn't saturate today. Yeah.
I mean, yeah, I mean,
Or you saturate, or whoever saturates first.
right, good. Okay, so we have this guy here, so I delete this. And then we have a Hamiltonian that is J S1 dot S2. This is the usual stem. Plus, in addition, we have this, I will call it B. Usually it's JXY. If it is anti-symmetric, it is called B. It is DZ. And okay, so we have DZ S1 X S2 Y minus S1 Y S2 X. And this is the anti-symmetric part. So you could also write this as a D dot S1 plus S2. This is a vector, this is a vector, this is a vector. So this is the usual term that you find in the Hamiltonian. And then what people do, and depending on if the people are, how careful they are, this depends on the direction of the bond. So usually when you have some material, then they will draw the arrow, maybe the DM is like, maybe it's pointing like that. And it's very important that they draw the arrow. So it's not enough, I mean, that, how should I say, this is 1 and 2, and you need to specify that it is going, I mean, the DM interaction is in that direction, and you need to, if what is side 1 and what is side 2. So if you see a paper where they don't specify, they just draw the DM vectors without specifying what is the first spin and the second spin, then you are in trouble because you need to figure yourself if it's plus and minus. So good papers, they all draw these things there. And that led to confusion. I mean, there was a social copy, and the first paper didn't put it, and then there was a big confusion about where that. So, okay, fine. Anyway, so we are here.
So here, hang on. So for this term, if I understood correctly, D vector is out of the plane, isn't it?
I think so.
So how would I draw that diagram for this situation?
What diagram?
Oh,
you would. Okay.
So you just draw this.
Like that.
Okay, so you draw 1, 2, and
yes,
then.
And you specify somewhere in the capture, whatever.
Okay,
Yeah,
okay, okay, got it. So it does not have to be from 1 to 2. That was just an accident.
Just an accident.
Okay.
That you need to specify. DM interaction. This is the vector, and there is this vector information that is from 1 to 2. Yes. Yeah, because that is anti-symmetric. Yeah. Right. Okay. So what is this? This is the volume. So this here. So you want to minimize the energy. The energy of this guy is minimal. Suppose we look at the classical spin. The energy of this guy is minimal if this is spin 1, this is spin 2, and they are pointing in the opposite direction. This minimizes this part here. What about this? What does this guy want? What it wants is to have a maximal volume that the D vector Sn. So if this is a D, right? So if this is the D vector here pointing somewhere, then the spin would like to be in the plane that is orthogonal to the D vector and S negatively S1 and S2. This is the thing that maximizes this DM vector, and the spins can, and this is one situation, but also equally well. This is also a good one, S1, S2. So there is one U1 symmetry remaining, O2 symmetry among the DM vector. So I'm the DM vector, we have the 90 degree, all these spin configurations there equally well. So it wants to optimize the volume. This has zero volume. So what it will cause is it will cause that the spins, if we add the two guys together, what the compromise will be that we will end up with two spins that are kind of like that. Because here they gain a little bit of volume, but still they are mostly antiferromagnetic, and then there is this ferromagnetic component appearing. Then this is for one bond, and then suppose you have convenience, if you want to see what you have here, a DM interaction that is maybe like that, then you would like the spin, this is like that. And then the question is, what happens for the next bond? For example, here we had this guy on above, but in the next one, it can be above or below. And if it is above, we just need to translate it. But if it is below, then the DM interaction will change the sign. And then what will happen is that the spins will come back. So there are two situations that we can imagine. So one case we have the copper, oxygen above, here oxygen above, oxygen below. Then here is it. So the spins then become coplanar, perpendicular to the DM vector. So this is the same here. But then we want to continue this in the same, the rotation in the same direction. So that would be maybe like this.
So spiral.
Spiral, this will be spiral, this will be staggered.
So the second case is very similar to like having inversion symmetry breaking locally, but globally it is preserved. Is that right? The second case.
Yes, we have a
Inversion center.
We have an inversion center at the side, not at the bond. That's correct. And because we have inversion at this side, then this spin will be, you're right.
So no DM between 1 and 3.
There's no DM between 1 and 3.
But 1 and 2 is allowed.
1 and 2 is allowed.
Yes, that's how to think about it.
So even though the total DM interaction is 0, because those are like opposite, still it can lead to kinetic.
It can lead to kinetic and to a ferromagnetic moment. Because you will generate effective moment here. Here you don't.
So can you please explain that 1 and 2 that maximizing the vector, but it can not be.
Say again, please.
That in the middle, that diagram on 1 and 2 that we cannot maximize.
So the competition between volume and antiferromagnetism, right? Yeah. Just explain it again.
Yes. Okay, right. So we have these two terms, and good. Suppose that let's do with the numbers. So and we have spin 1 and polar coordinates would be like this is a phi angle. So x1x is cosine phi, x1y is equal to sine phi. Okay, let's do this angle. And similarly, phi. Okay, and for the second one, I didn't know that it will be. We take the phi to be this one. Okay, so then the x2x is equal to minus cosine phi, x2y is equal to sine phi. Please check if I am not making the mistake here. Then the dot product is j times, I need to multiply this guy, it is minus cosine phi squared plus sine squared phi. This is the energy of the Heisenberg exchange. It's fine, okay. Then we need to calculate this thing here. So we have plus d times, and so my apologies, it has been some time that I'm just doing this. Okay, right, so what we do is 0, 0, d, z, and I need to put here the components of S1 x, which is cosine phi, sine phi 0, and here I put minus cosine phi, sine phi 0, and the determinant is cosine cos phi, sine phi 2 times. Is it right?
That's right. Yeah.
Okay, I passed. And this is the same thing as j times minus j times cosine 2 phi. This is right. This is plus d times sine 2 phi. So I need to optimize this expression here. And if I optimize this expression, I can get that the tangent of 2 phi is proportional to d over j or something like that. So this will tell us what is the optimal angle, how much is the tilt between the two guys. If the dm is 0, in that case they want to be really opposite direction, and the stronger the d is, the larger the angle is this canting angle. Good. Okay, yes.
For the when both of the oxygens are like above the connection bond, how do you put the split that third split?
Can you repeat please?
Sorry, for the case, there are three lattice points, right?
Oh, you mean here? Yes, right. So you're asking about this figure. How to know what is the dm interaction between 2 and 3?
Yeah, my question is for lattice point 2 and 3 when both of the oxygens are
Above.
like above the line, are those in the anti-parallel? Like 2 and 3? Like how do
Right. Okay, this is so what I'm trying to do. Okay, so you're asking me how did I know this figure? It is a tricky thing to do, and I hope that I did it right. So essentially, okay, right. So let's do it again. This, 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 and I started slightly different. Let this be here, this be here. Then this is above. We have maybe dm interaction like that. This is also above, yes, dm interaction like that. And then this would like, I started with this would be the antiferromagnet, but because of the dm interaction, I needed to kind it to gain this phi energy. Then let's go to the next one. The next one here, it is below. This is above. This is the same dm interaction. Here the dm interaction is pointing inwards. So if this is pointing inwards, if we just repair the tilt, the antiferro would be this one. If it is pointing in, then we had a tilt that was going in this direction, but this direction, but we need to reverse the direction, so it will come like that. So okay, once again, so we have this is the antiferro, and then I think in this clockwise. Then at this point here, the dm interaction has opposite sign, so I need to tilt anti-clockwise. So I go the anti-parallel and I tilt anti-clockwise like that. And then this is, I'm sorry, I'm not used to this stroke. very soft. Right. Okay. And what happens here is that I draw the antiparallel component. I tilt it clockwise, and I also need to continue tilting clockwise because the sign of the TM interaction is the same. So I will end up with this thing here. Is it okay? Okay, yes.
The down with the alternate oxidizing up and down. That example will have a spin that is like this, then it will rotate and then it will come back to
Yes, yes, that's correct. It will be
alternating between.
yes, it is a sort of staggered spin configuration, and the other one is a spiral.
Here we can see some kind of a spin wave.
Yes.
That also comes from the polar. These two are related. Like incommensurate lattice, then automatically comes into play because the periodicity of spin not equal to the periodicity of lattice.
Okay, so you are talking about metallic magnetism. I don't talk about metallic magnetism. You are correct. That that is more complicated very often. Nevertheless, and this is very important point that you made, that here we were only talking about the nearest neighbor exchanges, but it may happen that we have a chain, chain 1 nearest neighbor exchanges, and then we have a second neighbor J2 exchange, and they are both antiferromagnets. So if I would draw this, like antiferromagnet, then the J2 would be frustrated. This is not the optimal. So what the optimal is that again we will end up with a spiral in this case as well. So we will end up with a spiral that is like this, like that, and so on. That it will rotate. But in this case, the spiral, we have the plane of rotation, and it can be anywhere for the J1, J2 when we have a frustration and we have isotropic spin Hamiltonian. So the plane of this frustration, of the spin spiral can be in any direction compared to the chain. Here, the dm will cause the spiral to be, the plane of the spiral to be, like in blackboard. Yes. And this is very important because this will come the next. Right. Okay. I think I continue a little bit more. Sure. Maybe without break. Are you fine without? You want a few minute break, or can I continue? Who wants a break? Who wants a 5-minute break? Okay, you're getting hungry, so let's finish this as soon as possible. Okay, right. Understood.
So one question.
Yeah.
So normally, the fact that time reversal operator squares to -1 is important in some context.
Yes, it is.
But here it is not important.
It's not important because we are dealing with string operators, and string operators are quadratic kind of in spin 1/2. So we always have, what we are doing here, we are measuring like up. You can write the SZ operator like up, minus down, down, and they come in pairs. What you are saying is very important, and this is what I was hoping to tell. In my mind, I was much faster, and I was thinking to tell you about hopping. What happens if we have a spin orbit coupling and hopping of electrons in the Hubbard model? In that case, what Sumiran is asking, there will be C-dagger operators, not spin operators, but C-dagger operators. And the C-dagger operators, when we transform under time reversal, then they can get additional minus sign.
Right.
Yes, we will see. Yes, that's very important. These are the double groups. But this is, so far, I didn't touch that problem. Right, so spin orbit coupling. What is the spin orbit coupling? So, so we have a nuclei, and the electrons, they have their own spin, and they are rotating around. I think doing something. Right, so they are going around the nucleus. If I sit, with me, I sit on an electron, I travel, I see that the nucleus is kind of a charge that is having some velocity. And if we have a charge that has some velocity, it will generate some magnetic field at my side. It will feel like that. And if there is this magnetic field in my reference frame from the nuclei, my spin will just act with that magnetic field. There will be the same coupling. So here's a B that is kind of generated, and which is roughly V cos E, and then this C squared or whatever, so this is by this characteristic. So there is a local field, magnetic field, that depends on velocity, my velocity of an electron, and the electric field that is at that side coming from the nuclei. And then this B will act with the magnetic moment. This is a Zeeman coupling that has been experimentally measured. You have a magnetic field, then an electron with a magnetic moment mu. This will be the energy if we try to align or anti-align with the magnetic field. So this will be the Zeeman coupling, and this B, I will experience an energy, Hamiltonian, where this B mu, because of this B mu, there will be some Hamiltonian that is V cross E. Sorry, I learned to, the vectors are usually be underscored, and this not an arrow. So what I meant is, I think what you do is usually you do that. Is that right?
Where are they underscored? You said you learned underscore?
Yes, in the university we did everything with underscore.
Okay.
It's easier because this needs more.
Well, true.
Also,
Yeah.
right. Okay. So this, and then this is something like, sorry, n times mu. So there will be a term like that in the Hamiltonian. Now E is a radial electric field. This is the E. So E is roughly proportional to R vector divided by some maybe like that. Roughly, hand waving, by hand waving. So this would be something like V cross R divided by R cube dot V. Okay, something like that. V cross R, if we divide by M and multiply by M, this is the momentum of the electron. So this is something like, this thing here is like L, the magnetic moment of the electron, the orbital magnetic moment of the electron. So we end up with L dot mu, but mu is again proportional to the spin. So we end up with this LS, and then there are some stress factors here that include the G factors, whatever, I don't know what they all contain, but this is the most important part. An electron will feel the orbital moment it is in. Okay, this is one piece of information that we need. The second piece of information what we need is that, that if we are in a crystal, so in the space, if we put an electron, if we put a transition metal, then all the d electrons, there are 5 d orbitals, all the 5 d orbitals will have the same energy. Now, if we construct a crystal, in that case, the crystal will have some environment. So earlier here, there was the T-type model. The T-type model is made out of transition metals that sit in the cage, octahedral cage made of oxygen. So there is a static electric field at the site of iridium, and that will split the degeneracy, the 5 of degeneracy of the d orbitals. So it is something like that, that we have the 5 d orbitals, these are the d orbitals, and then in octahedral crystal field, if we put in octahedral, there will be something that will cause these orbitals to split into 2 sets. This will be called E2G, and these are called EG orbitals. For example, if we look at suppose we have or maybe we take a cube. We don't really have cubic, this type of cube, environment, cage, but it is easier for demonstration purposes. So, the d orbitals, we can, x, okay, so d orbitals, they are like r squared times the y to m, something like that. So they are quadratic in the x, y, z.
Of the crystal field, it will be other way around.
It's possible. Since this is being recorded. Right, thank you. So, these are they will be some polynomials of x and y and z. So it can be like x dot y, not xz, y z, x squared minus y squared, x squared minus z squared, y squared minus z squared. I think these are all possibilities, but then we have too many here. So these are not linearly not independent, and what happens is that we will add these two together, and then we will end up with something that is called 2 z squared minus x squared minus y squared. So these are 5 d orbitals that we can think about, and some linear combination will optimize the electrostatic energy, because this is a cloud of electrons. So if we write xy, it will be like, if this is the xy plane, then the orbitals will be like, this is the amplitude plus.
Maybe along the diagonals or something.
Yes, mistake. Yes. Right.
She's the expert, really.
Yes, of course. Very good. Right, so here, and we have a plus, minus, but the charge is the absolute value squared. So the charge is, there will be lots of electrons here. And if we have the electric charges around, okay, we need to put it into the cube, then you see that if we have xy, or we have the yz or xz, they will be essentially the same thing, just rotating if we look it from the different directions. So this will be the xy, xz, yz orbitals here. With the remaining guys, it is not obvious that they will have the same energy, but you can act with the generators or the group elements of the cubic group of these guys. And what will happen is that if you add something on this thing here, it will maybe become, maybe we do a C3 rotation on one axis, it will become like y square minus z square, and then you can write it as a linear combination of this guy and this guy. And then it will, you will see that x minus y square and the 2z square minus x square minus y square, they are wave functions that I have over there. Okay, so we have this splitting here. If we distort furthermore the cube, like we stretch it a little bit, then what will happen is that there will be additional splitting of levels, and I don't know what happens to the EG, but definitely these two guys, they will also split into two. Okay. Now, these are the energy levels. That's how we think it. Yeah.
Could you please repeat the argument for why the x square minus y square and the other are degenerate, or at least how you sort of said it?
Okay, so then the cube. We can make one. This is a. This, I mean, from the center to one of the corners of the cube, this is the one direction.
Right.
We can, the cube, if you look from the one direction, you can see that you can rotate by a free-fall rotation. Then it is a C3 axis.
Right.
It will move x to y, y to z, and z back to x. This is the C3 rotation of the cube. This is what it does. Then if I have this x square minus y square wave function, it will generate from x it will make a y, from y it will make a z. It will make this one, but this guy is not a new thing. It will be just a linear combination of these two guys.
Right.
And then you can write it as,
it's some linear combination, alpha.
X square minus y square plus.
Some alpha beta.
I was looking for help.
That's okay. How does this imply degeneracy?
This is a two-dimensional irreducible representation. And if you have a two-dimensional irreducible representation, okay, you don't know that this is a two-dimensional, but you can figure out that it is indeed a two-dimensional irreducible representation, and then this will be for the general.
Okay, so it's a symmetry argument.
It's a symmetry argument.
Not
symmetry. So you can try to do. I mean, okay, you can play a game. You can put it into your mathematical notebook or whatever. The positions of the charges here. Calculate what is the local electric field here, and you try.
No, I got it. Yeah.
You get that.
So maybe another way of saying it is, say I take x square minus y square.
Yes.
I do a C3 to get y square minus z square, but that should have the same energy.
Yes.
And you get the third one, which is z square minus x square, which will also have the same energy. But 2z square minus x square minus y square is made up of these things. So therefore, it must also have the same energy.
Yes.
Does that make, is that roughly correct?
I believe so.
Okay.
I'm already here.
Yeah, that's fine.
It's a complicated argument, but I think it's fine.
Right.
I believe you.
Yeah.
Okay, right, good. So, and then, so there is this energy level, but then there's also the L. We need to calculate what is the spin orbit, what is the orbital moment in these cases. And to do that, we do the L is actually, and here again, I don't have to make a mistake. Here, that is I. L is I, then derive minus phi is Z, and Ly is just to the cyclical rotations. And then, if you know these operators, they will also satisfy, by the way, the algebra. And then you can ask that you put these orbitals, and you can do like Lx, xy, by the things like that, you can calculate these matrices. You will end up with a 5 by 5 matrix. That 5 by 5 matrix also satisfies the commutation relations of the orbital of the angular momentum, and then, but it will be, there will be a 5 by 5 matrix that if you diagonalize, it will be, if you, okay, depends on, okay, you don't diagonalize, yes, fine. So you can write the LS. You have a 5-dimensional of the L, and then somehow you need to take another 2 dimensions for the spin, so it will be another 5 by 5, and then this is the L part, this is the spin part kind of. You have got a 10 by 10 matrix, and if you diagonalize, you will get the L plus S is L plus 1/2, say you have only single electron, then it will be L plus 1/2 plus L minus 1/2. This will be the total angular momentum of the spin and the orbital moment. So it will be L of the d electron is 2, so we will have a 5/2 and a 3/2 effective moment. And it will be 6-fold and 4-fold degenerate. Now, once you introduce the crystal field, this degeneracy will split. And it won't be anymore, the J is not anymore a good quantum number. And then it means that somehow, if the J is related to the isotropy in the space, it is not anymore good one. So we establish here the crystal field, and these operators, the spin becomes coupled to the real world. Good. Now it is 12:15, and I think
maybe we can stop. Yeah.
Yes, some people are already leaving.
Yeah. That's a good time. I think everyone is saturating. But maybe we can quickly recap this in the beginning of next time.
Definitely, because I will use this to derive you some real interaction.
So one question before the LS coupling. So we got this T2G and EG.
Yes.
And if I just do this calculation of L in that, is T2G L equals 1 or no? It is ill-defined. Not good under L because it is due to crystal field splitting.
Okay, so good. Very, okay, so good. Maybe a few more minutes.
People, if you want, someone wants to leave, feel free to leave.
No, don't leave.
Okay, don't leave.
Don't leave here.
Since we have held you hostage, so therefore you are holding it. Hostage. Fair enough. Yeah.
So this we want to calculate the L in this EG T2G manifold, and let's only look at what does it look like? So suppose this is the EG T2G block, and this is the EG block.
Very good.
And we are integrating L.
Right.
Then what we will get is there will be 0 here. Again, I will need to check. Okay. There will be something here.
I see.
Some octagonal elements.
Okay.
The crystal field energy separates them, so we don't care about what is there. And what remains here, it will be something that there will be off-diagonals, and x will be between 0, 0, 0, 0, and there will be maybe I and minus I. I am not sure.
Okay.
I think. Okay, there will be something. So we will have a 3 by 3 matrix that looks very, very similar if we would do the helix matrix elements between the p orbitals. The p orbitals are n equals 1, and if we calculate the same helix for the p orbitals, we would get the same thing, except there is a sign change. There will be, if this is for the T2G, for the p orbitals, it would be like that. If we repeat this for L by Lz, the i's will move to the corresponding sides. For the p orbitals, these 3 by 3 matrices will satisfy the usual Lie algebra. For the T2G orbitals, these 3 by 3 effective matrices will not satisfy the real algebra. They will satisfy with the minus sign.
Mhm.
So we have a very weak situation
Mhm.
that the L of the P2G is just kind of a minus
Mhm.
proper L operator. So
Modulo these off diagonal matrix elements.
yeah, I mean we forget about that.
We are
So
forgetting.
if we put them back,
Yeah.
then it will
It's a
be a
mixture.
proper equal to.
Right.
I mean,
Right.
If you look at the commutation relation, it will be
Right.
a proper
Right.
algebra with a
Right.
of
Right. Right. Of
N
course.
equal to. But
Right.
this guy is not. It is just a minus kind of looks like kind of a you know, you rotate your head in this way, but the guy is rotating it the other way.
Mm.
Weird.
Mm.
Good. So this is something very special about the D2G
I
orbital.
see. I see.
Yes.
And this physics can be relevant if
It's very relevant.
uh,
Irritates.
for irritates it's relevant.
Yes.
Bec-
Yes.
But for it to be relevant, we need that matrix element, the off diagonal matrix elements, to be less than the so this is crystal field than the spin orbit coupling. Is that correct? I'm just getting a little confused about what is the role of the off diagonal matrix elements and the scale that it brings. Yeah.
Okay, they will have some correct. I mean, you can do the
Uh-huh.
you can work it. I mean, you can introduce the lambda for the spin orbit coupling and this crystal field, and you can work out the
Okay.
how the energy levels go and what are the wave functions and things like that.
Fine. I'll ask you later. Yeah.
Yes, but it's very important because this minus sign. I mean, the total magnetic moment that we measure is equal to G of L plus G electron S.
So the
And if this G is equal to 1 for orbital, this is equal to 2. And if this L is kind of minus 1, and this is 1/2 is also 1, so we end up that we have states that are not magnetic. I mean, we have some L finite orbital moment, but they don't show any magnetism. They're difficult to see with neutron scattering, whatever that would interact with magnetic moments. Yes, right.
great.
Thank you.
Thank you, Karlo. We can end it here for today. Let's give a round of applause.
And I hope you come.
Yeah, we'll continue this on Friday.
Any feedback, welcome.